The scenario involves three houses constructed simultaneously where House C experienced a failure in the electrical inspection process. Specifically, the electrical rough-in inspection was not performed before the subsequent phases of frame, insulation, and drywall were completed. This oversight was not identified until the electrical final inspection was requested. The resolution involved an engineering letter costing $800,000 and arc faulting the entire house to obtain clearance. The primary responsibility for ensuring all inspections are completed and signed off prior to proceeding with subsequent trades lies with the contractor. In this case, a contractor neglected to verify the electrical rough-in inspection before calling for frame and insulation inspections. The county inspector also bears responsibility for failing to inspect the electrical rough-in despite having the opportunity to do so. The inspector repeatedly missed the issue during subsequent inspections, including the frame and insulation stages. The electrical contractor may not be held liable if they were not notified of the delayed inspection or given the opportunity to correct the issue before drywall and finishing. The impact on the electrical contractor includes time and labor costs associated with arc faulting the entire house, incurring additional expenses. The contractor may also face reputational damage due to the delayed inspection and subsequent issues. To prevent similar incidents in the future, it is recommended that the contractor implement rigorous inspection protocols to ensure all trades are signed off on before proceeding. A contractor should establish clear communication channels with inspectors and trades to minimize missed inspections. The county should review its inspection procedures to identify and address any gaps that may have contributed to this incident. The county should provide additional training to inspectors to emphasize the importance of thorough inspections at all stages. The electrical contractor should document all interactions with the contractor and inspectors regarding the delayed inspection and consider filing a claim with the contractor or county for reimbursement of reasonable expenses incurred due to the oversight. Let's consider a hypothetical electrical system to illustrate the principles at play here. Imagine a house with a 200 amp service entrance. This means the main breaker at the service panel is rated for 200 amps. The National Electrical Code, or NEC, dictates requirements for conductor sizing, overcurrent protection, and grounding. Let's focus on branch circuits. A typical 15 amp circuit, used for general lighting and receptacles, requires a minimum of 14 American wire gauge, or AUG, copper conductors. The overcurrent protection device, which is the circuit breaker, must be rated for 15 amps. A 20 amp circuit, often used for kitchen appliances or bathroom receptacles, requires a minimum of 12 AWG copper conductors. The circuit breaker must be rated for 20 amps. Grounding is crucial for safety. The equipment grounding conductor, which is typically a bare or green insulated wire, provides a low impedance path for fault current to return to the source, tripping the circuit breaker into energizing the circuit. The size of the equipment grounding conductor is determined by the size of the circuit conductors, as specified in the NEC Table 250.122. Now let's discuss arc fault circuit interrupters, or SICE. These devices are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. An arc fault is an unintended arc created by a current flowing through an unintended path. SIs work by monitoring the current waveform in the circuit. They can distinguish between normal arcing, such as that caused by a switch opening or closing, and dangerous arcing, such as that caused by damaged insulation or loose connections. When an SI detects a dangerous arc fault, it quickly trips the circuit, interrupting the flow of current and preventing a fire. The NEC requires SIs in many areas of the home, including bedrooms, living rooms, and hallways. Returning to the scenario, the fact that the entire house needed to be arc faulted suggests that there may have been concerns about the quality of the electrical work or the presence of potential arc fault hazards. Arc faulting involves systematically testing each circuit with an SI tester to identify any circuits that are prone to arc faulting. This can be a time-consuming process, but it is necessary to ensure the safety of the occupant. The $800,000 engineering letter likely involved a qualified electrical engineer reviewing the electrical system design and installation to ensure that it met all applicable codes and standards. The engineer may have also performed calculations to verify the adequacy of the wiring and overcurrent protection. The engineer's letter would have provided assurance to the inspector that the electrical system was safe and code compliant. Let's consider the grounding electrode system. This system provides a connection to earth, which helps to stabilize the voltage and provide a path for fault current to return to the source. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or metal water pipes. The grounding electrodes must be properly bonded together and connected to the service equipment. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, as specified in the NEC Table 250.66. Bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a low impedance path for fault current to return to the source. This includes bonding the service equipment, the metal enclosures of electrical equipment, and the metal water pipes. Bonding helps to ensure that all metal parts are at the same electrical potential, which reduces the risk of electric shock. The size of the bonding conductors is determined by the size of the circuit conductors, as specified in the NEC Table 250.102. Overcurrent protection is essential for protecting electrical circuits from damage due to overloads and short circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a safe level. Circuit breakers are resettable devices that can be tripped manually or automatically. Fuses are one-time devices that must be replaced after they blow. The size of the overcurrent protection device must be properly matched to the size of the circuit conductors. Voltage drop is another factor that must be considered in electrical system design. Voltage drop is the decrease in voltage along a conductor due to the resistance of the conductor. Excessive voltage drop can cause equipment to malfunction or overheat. The NEC recommends that voltage drop be limited to no more than 3% for branch circuits and no more than 5% for feeders. Wiring methods are also important. The NEC specifies different wiring methods for different applications. Common wiring methods include non-metallic sheathed cable, or NM cable, which is commonly used for residential wiring, and electrical metallic tubing, or IMT, which is commonly used for commercial and industrial wiring. The wiring method must be appropriate for the environment in which it is installed. The NEC also addresses the installation of electrical equipment in hazardous locations. Hazardous locations are areas where there is a risk of explosion or fire due to the presence of flammable gases, vapors, or dusts. The NEC specifies special requirements for electrical equipment installed in hazardous locations, such as explosion-proof enclosures and intrinsically safe circuits. Let's also consider the requirements for electrical boxes. Electrical boxes are used to enclose electrical connections and protect them from damage. The NEC specifies the types of electrical boxes that are permitted for different applications. Electrical boxes must be properly sized to accommodate the number of conductors and devices that they contain. Conductor fill is another important consideration. The NEC specifies the maximum number of conductors that can be installed in an electrical box or conduit. Exceeding the conductor fill limits can cause overheating and damage to the conductors. The NEC also addresses the installation of luminaires, or light fixtures. Luminaires must be properly supported and securely attached to the building structure. The NEC specifies the minimum clearances that must be maintained around luminaires. The NEC also contains requirements for swimming pools and spas. The electrical equipment installed near swimming pools and spas must be specially designed to prevent electric shock hazards. The NEC requires ground fault circuit interrupters, or GFCIs, for all electrical circuits serving swimming pools and spas. Let's talk about ground fault circuit interrupters, or GFCIs. These are crucial safety devices designed to protect people from electrical shock. They work by monitoring the current flowing in a circuit. If there is a difference of even a few milliamperes between the current flowing into the circuit and the current flowing back, the GFCI will trip, quickly interrupting the power. This difference in current indicates that some of the current is leaking to ground, which could be through a person. GFCIs are required in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor receptacles. The scenario highlights the importance of proper communication and coordination between the various parties involved in a construction project. The contractor, the inspector, and the electrical contractor all have a responsibility to ensure that the electrical system is installed safely and in accordance with the NEC. When communication breaks down, as it did in this case, it can lead to costly errors and delays. To avoid similar problems in the future, it is important to establish clear communication channels and to document all interactions. The contractor should verify that all inspections have been completed and signed off before proceeding with subsequent phases of the project. The inspector should perform thorough inspections at all stages of the project. The electrical contractor should promptly report any concerns or discrepancies to the contractor and the inspector. In summary, the electrical contractor may have grounds to seek reimbursement for the additional expenses incurred as a result of the missed inspection. The contractor and the county share responsibility for the oversight. Implementing rigorous inspection protocols and improving communication can prevent similar incidents in the future. The NEC provides detailed requirements for electrical installations to ensure safety and prevent hazards. It is essential to adhere to these requirements and to consult with qualified professionals to ensure that electrical systems are installed properly.